Welcome to the GOTO podcast. Each episode covers the brightest and boldest ideas from the world's leading experts in software development. Tune in for practical lessons, compelling theories, and plenty of inspiration. GOTO gathers the brightest minds in the software community to help developers tackle projects today, plan for tomorrow, and create a better future. Stay up to date with the latest in tech through GOTO's top-rated events held online and in person in cities like Amsterdam, London, Copenhagen, and Chicago, and by subscribing to the GOTO Conference's YouTube channel, where you can find thousands more high-quality dev talks. Learn more at gotopia.tech.
Hi, I'm Kirk Pepperdine, and I am a principal engineer working at Microsoft. And with me, I have Monica Beckwith. She is also a principal engineer working at Microsoft. So we do work together. That's our disclaimer at the from the beginning. And I know that Monica has spent an inordinate amount of time. Would you say years?
Writing the book, or just
just writing this book. What do you call it? JVM Performance Engineering. That's just been published. So congratulations on getting that out of the out the door. because I know you spent a lot of a lot of time. Well, the book has been in the making for quite some time, and I guess we're here to talk about it.
Yes. Thank you for having me, and thank you, Anka, for getting this going. I know we've been, the book came out earlier this year, and then ever since then we are trying to get together to have this kind of GOTO series. This be a part of the GOTO series, and I'm glad that Kirk gets to be the one not only asking questions but also work with me on this, because it gets very comfortable if we both know the space, and Kirk is one of my mentors, so I feel very honored to be here.
It's so kind of you to say. Well, it's safe to say that we push each other and learn a lot from each other in the process. So I guess the first question I had on my list of questions here is why this book and why now? I mean, there's a bunch of performance books out there written by a number of different people. And, what's in this book that you thought you could bring to the space?
Yeah. And I think, it's kind of, and I've covered this in that, in the preface of my book. This book is an ode to my to JVM performance, and that's what the book is about. So in the sense that it's a journey, and as the poem says, it's my tech odyssey, and and it kind of builds on various JVM systems that I've worked with in my lifetime. And I'm kind of like a bard singing tales of heroes and their exploits. So I'm kind of in talking about the evolution of the JVM through the lens of performance engineering. So we conceived this book around the time of this transformation of the JVM and the JDK, right? So the Java 9 was on the horizon, or almost released, and that's when the book was conceived. And what I saw, it was kind of a shift. And the new plane now was the world of modularity and microservices. So it's kind of like it extends beyond the deployment practices, but also explores the JVM and the JDK itself. So it talks about the evolution, like I said, of the JVM and the language. It also talks about the type system and its evolution. And then I talk about the modularity. So, and how that influences not only the application, like, the use case of Java, but also the JDK itself, how it has gotten modular. And it kind of builds on that and kind of, kind of weaves in performance engineering practices. So we talk about logging, I talk about performance engineering principles, the approach, and then I dive into the memory management, the runtime, and kind of like startup and warm up phases, and how that all ties into the future. That's just the way it evolved. The book evolved, and it's a journey of how I evolved in the field of JVM and performance engineering as well. So we're working together with so much things, and the JVM has such a big impact. And trying to look at it from the performance engineering lens is something that I wanted to provide. I'm not sure if many books out there, which are all great in their perspectives of deployment, but I wanted to give a under the hood perspective of the JVM, of what performance means and how do the various components kind of work together to make the JVM as performant as it is today, and what does the future look like. So that's kind of why I thought the book was much needed, to provide that, to as an advocate of the JVM and performance engineering. So that's my perspective that I bring into the book.
So, but then why now? Have things changed considerably since? Well, you said you started this process in when JDK 9 was coming out, and from a performance engineering point of view, it's what's changed since JDK 8?
Yeah, great question. I think a couple of things changed. In the GC world, we started seeing that, wanting more control over, how we manage and define pauses, GC pauses. We went in the route of regionalized and incremental collection. From the JDK perspective, like I said, modularity is at the core of our JDK. Security, encapsulation, those are becoming the the grounds up approach that we have brought into the JDK. From the runtime perspective, we're talking about going into Project Loom space, virtual thread space. We are evolving in that, or sometimes we are refining in that, and this is all from the performance perspective. These are asks of the ecosystem, microservices, containers, cloud. These are demanding a growth in the JVM space, and the JVM is delivering that. We're talking about cloud native now. So cloud native is a big deal, and how is JVM at the center of this cloud native revolution? So all these things are something that I think drove to the book to what it is today. But also my personal my personal need of the book was I wanted it to be educational. I want performance engineering to be approachable, and approachable not only for students. My kids are these students, so I want my kid to pick up the book and go step by step, and at least understand the approach to performance engineering, and then hopefully they will be working with the programs. The programs are real. The examples that I provided are real world examples, like you and I can relate to, and I hope students can relate to that. It's also something that I wanted to write. I wish I had this when I was a developer, a programmer. Wish I had an approach to JVM engineering and performance engineering kind of amalgamated together. I also want this to become like a part of our university curriculum. When you learn about software engineering, I want performance engineering to go side by side. So we have a holistic engineer that the next generation that understands the concept of experimental design, right? that understands why hardware is so important. We can, today you can spin your container and somewhere in the cloud on some machine, and you, end up deploying it. And, that's not the end of the story. That's just the beginning of your code is just the beginning of the story. And that's what I want people to take out of this book. So I think the timing was right. And I think here we are.
Yeah, that's so adding more resources like this to the space actually, I think, helps with the educational process, because it's traditionally something that universities haven't really tackled all that well. In my experience, what we tend to see is that you'll get a lot of education in algorithms and how things work, but very little in the diagnostic space, or how to break problems down, especially when things aren't working.
Yeah. And, kind of demystifying the JVM. I mean, JVM is not just a black box.
It's a piece of software.
Yeah. And what does that mean? And how does your software affect this other piece of software that works on this hardware, or through various stacks, works on this underlying hardware? And how do they all interact and work together to give you the performance that you need? So and also what is performance engineering is like the biggest thing too, right?
That's my next question is it's like, what is performance engineering? How do we define this space? Yeah.
I've given many presentations on this, and one of so I keep asking myself this question, just not only the first time that I actually gave a presentation on performance engineering, but every day, as I'm refining my presentations on performance engineering. So I think it's just, I could define it as a systematic approach, right? And it's kind of ensuring that the systems, whatever system, the software system or the design system, kind of any system that you design meets kind of the broad range of non-functional requirements. So you're designing a system for functional requirements, but there's this whole non-functional component that kind of is the big umbrella of performance engineering. So I kind of refer, I've given many presentations on this. I refer to this as ilities, which is like the scalability, reliability, availability, maintainability, security, all these things kind of become the non-functional requirements that we need to tackle. Some of them, tie in with your functional requirements, and some of them are something that you add on to your development lifecycle so that your system can meet the service level objectives and agreements. But the main thing that you have to understand, that we all have to understand, that any component that we design, has to enrich the user experience. And I recently gave a presentation of step-by-step in Java with performance engineering. And one of the biggest thing is that how are we doing with respect to the user experience? So SLAs, the functionality, even the maintainability, availability, all these things ties to the user experience. The end product is delivered to a user or for a user, and how do we enrich that experience? So that's my definition of performance engineering. It's about being proactive, kind of, designing the test and then continuous improvements, just like you would do for your software development lifecycle. It's the same thing, and it's an integral part of that lifecycle. Kind of. And through this book, I hope people bring that into their, into the very early stage of that life cycle, kind of so that your systems are more reliable and efficient, and kind of like a holistic approach to software and performance engineering.
Yeah. So how does this tie into observability then?
Yeah, that's a very good question. I think measurement ties into observability, like the way that we have a component, and how does that component, first of all, integrate into the bigger picture? How do these subsystems uh, talk to each other, and how do these when a process is deployed, then how does that work? And all these things are that the answering the question how, and the question what, though that's where observability helps us, right? So how, you observe it, and then and the what is what you get out of the observability data, and that's how you explain the what. So it's kind of an you know performance engineering is all about how, what, and the why, right? And so why, we'll figure it out, but the how and the what is where observability plays a big role. And you, Kirk, have a lot of experience in that space, so if you have anything to add on, please do.
Oh, well, it's not. This is not so much about. I mean, it's. I think in your book you touch on observability in a number of different areas, and yeah, I think it's an important aspect of a system, obviously, and I like how you dress it in the sense that a lot of people don't take into account the impact that observability has on the performance of their application, and and I think part of the performance engineering in my mind is understanding what that impact is and trying to minimize it. So from my perspective, I want to drive a particular behavior, right? And the data doesn't have to be perfect in order to drive that behavior in many cases, right? So we look at observability as basically being a property of the system. It's like, how can we easily get that information out of the system, and then again, how can we use that to drive the behaviors that we want in terms of like you said, discovering what and then why, so that we can take action to improve. Yeah.
Yeah, yeah, exactly. I think it's all a part of the fabric, and we're building the story,
Right.
and that's where these kind of mesh together, and then we get to the why.
Yeah. Eventually you get to the why. Generally not in one step, but you go stepwise
No,
towards.
no, and that's it. It's an approach. I mean, performance engineering is a learning approach, right? Or approach to learning in that sense.
Right. You're learning about the behavior of the system. Yeah, and
Yeah,
it's rare that you go from. I think it's rare you go from like a single data set to that's the problem that we need to be solving. I think
exactly.
there's some gradual step towards it. I think, yeah,
Yeah,
in my
yeah.
experience, yeah. So cool. Well, I guess the other like soft question we have here before we get into the really fun ones is like, what led you to performance engineering? It's like what is your personal journey from a high school student who typically doesn't know anything about the world, doesn't know what they want to do, to all of a sudden, here I am, a performance engineer. It's like, what does that journey look like for Monica?
Yeah. Yeah, a high
And
school.
more, I guess more importantly too, it's like, if somebody's interested in this, is, how do they get started? So what from your experiences can you share to say, hey, if you're interested?
So my performance engineering journey, to if I sum it up, it's like I don't know much, and that's how I started. I don't know, and I want to know. Is like that's and still today I'm learning. Every day we do something, we work together, Kirk, and there's like so much learning in daily in every new aspect of what we're learning with respect to the Azure stack, with respect to our own needs to help our first party partners. And we're learning the various technologies that are very new to me, especially being working in a different domain, but now looking at Windows and looking at the hypervisor, because that's very again, it's different layers of performance engineering, and we still keep on. Every time feel like I'm building new layers and finding new performance problems. That So it's very exciting. But I do want to emphasize that it is, to me, it was a very natural progression. I never like set out, as you said, like a high school student that's like, I'm going to be a performance engineer. It was never like that.
I'm going to be in middle management. Right?
Exactly. Yes.
Very
It's
good.
but then I feel that I was always meant to end up here, because it was so natural that it was like, yeah,
You're
I should have told that high school student that this is what life was supposed to be for you anyway, like, because it's just a part of me now, I feel. So I started with embedded systems, right? When I started working, and it was about designing and conforming to military standards. So the performance and the operations against these very restricted operating conditions were key drivers of my design. And kind of this experience kind of taught me to empathize with the design board, kind of ensuring failovers and availability, especially of the comms, the communications, right? And we're out there, working in these harsh environments, and comms fail. What do we do? What's the backup? What's the time for availability of that? All these things became, and this is from the get go, like from the very.
That almost sounds like life and death in that case, right?
Yeah, it was a project that involved sonars and other things, and so I was on the electronic side of it. So it was very important to be able to get the information and communicate it, so that it was an unmanned system, uh, uh, or unhuman system.
You mean like a drone?
I'm not going to divulge details, but
Yeah.
we want to make sure that we get the data when we as soon as we see something, and it was really important. So uh, so kind of that empathy kind of drove me to design this robust system, and it had custom OS, custom code, programming, microcontrollers, communication chip, all those things was very custom. And
Yeah.
so again, tying back to the why, the what, and the how. So I started the other way, started with the why, like why do I need to do this, and then moved on to the how, like how do I do this, and then the system, the design system with the software, everything became the what. This is the
Yeah.
what, and so it kind of like the three things, how, what, why, they kind of keep on becoming the core of my journey, and they still drive me today. And it was very interesting because after that I kind of went and started doing after that work, for a brief time I did my master's, and I took up a job with the Center of Astronomy and Adaptive Optics at University of Arizona. And there the focus was on precision. It was
Yeah.
about
Really
electronic
different thing.
boards, yeah, and mechanical actuators, and the design of the secondary mirrors, and how it's such a complex system, like just the astronomy part of it, the adaptive optics part of it, but even the mechanical and electronics and everything, it kind of comes together. And it was so thrilling to be a part of this whole again, the we're trying to remove out the aberrations in the atmosphere when we're capturing a picture. And so again, the what and the why, and then the how we're doing it. So, right from designing and cooling down the actuators, which was the chiller system, to the electronics board, to the communications again, like how we're doing the communications. So I was a part of all those things, and it kind of taught me another performance engineering viewpoint, and then of course the whole history starts from the history with JVM and performance starts from when I joined AMD. And I was very fortunate to be a part of this groundbreaking work that was brought to mainstream by AMD. It's called the NUMA, non-uniform memory access. And these kind of the subsystem and the 64-bit addressable and data space, the 64-bit processing. So we're now bringing compilers and JVM into the 64-bit mainstream land, and teaching everything to speak the language of this, not just the addressable space, like I said, but the performance and scalability of the NUMA systems, right? So just understanding what the application is supposed to do, you know, again, just understanding the what wasn't enough. We needed to go into the how do we do this, like deep dive into how these instructions actually, get into and get processed by the system, by the hardware, by the architecture, how the data is brought in with through the multi-layered subsystems, and then kind of bringing in the why, like why are we doing this, and how can we make it better. So kind of working with those three principles again, uh, driving performance and kind of anticipating issues, and looking at the processor pipeline. We call it front end and back end. So that encompassed both these aspects. And yeah, and then it was never no looking back.
No, I guess, yeah, this is kind of weird. We've had, I guess, some similar experiences, and well, but quite different, I guess. But uh, I remember my first, yeah, first conference, I guess, like work internal related one where I was working at, and one of the guys in the group started with this list of names on slides, and he just columns and names, slides, flip to the next one, column names on slides, flip to the next one. He did this a few times, right? Just flipping through the slides, so just columns and names. And he said, these are the peacekeepers that have died in these places, and our job is to make sure this list doesn't get any longer. And at that point, you just, something like that was just so impactful. It realized that, what you did in terms of performance or reliability really mattered, could really, really make a difference, I think. From that, from my perspective, I looked at it and said, okay, that's transformative in the thinking about, not all systems are like that. I mean, certainly if you're buying your, ordering your lunch from, I don't know, your food delivery system, it's a little, not quite the same thing, but it's still, it sets a mindset, I think, where you said, okay, the systems do need to be reliable, because they, in many cases, they can have significant impact on people, I guess. And I think your astronomy thing was really cool, because now you start talking about different hardware components and trying to get everything to work and everything, and it sort of leads into the next question I had, which is like, how important is knowledge of the hardware? Why should we care? A lot of software developers will say, yeah, I don't really care about the hardware. It's not my thing. And I don't actually disagree with them from that perspective. But I think at some point in time, we do need to care, and, so what would you say about that? Because, I mean, you're talking about working with ARM, so I think that's low level. Right now, I think you're debugging chips, right? So
one of the things I wanted to go back to what led me to performance engineering, and that's one of the things that I've been very thankful of in the book as well, is I was fortunate to have mentors like you, Kirk, and Charlie Hunt, and who guided me through this journey. In the sense that your insights, when I went to your talks and when I worked with Charlie in early days at Sun, actually since AMD and then Sun and Oracle, it's I just kind of just looked at you and your presentations and your talks, and I just absorbed like a sponge. I was like, oh wow, I didn't even because you're working so close to the JVM and working so close to the hardware and everything, when I go and see these kind of deployment scenarios that I didn't envision, I was like, oh, wow, there's so much to learn. So it kind of like the complexities of performance tuning and optimization, you all were the pioneers of kind of getting people like me interested and then wanting to make the JVM better. It's kind of came back to I was lucky enough to work in the open JDK space before it was open JDK space, Sun JDK, and kind of bringing your experiences and kind of working hands on with the JVM, kind of making it work for everybody that has shared those experiences. It's really became a fundamental part of what I wanted to do and how I wanted to shape my performance engineering journey. So thank you. And yeah, for those that I've not mentioned in my book, I want to say thank you, performance engineering. I've learned from you all so much, and we've worked together in so many spaces that it's humbling. So thank you. Yeah. So now going back to your question of the hardware.
The hardware. Yeah.
Yeah. So it's been so my journey is the most fascinating part of it is that we have this piece of hardware, right? Or we are almost, that's where I come in. I'm not the verification or the chip designer or the subcomponent designer, the SoC designer. I come in that this is what we have. This is what we can do over the next couple of years. And we want your feedback. We want to see how applications and various components, especially the compilers and the JVM, what we need to change, what we need to enhance, and how can these subsystems benefit from this stuff that we have today, and how can they benefit from what we're going to do tomorrow. So that's where I come in. So it's not just about let's go play with this, but let's identify scenarios where this is going to solve a real problem. The presentations that I was talking about where you, Kirk, said, oh, this, I encountered this and the addressable space, back then even though we had 64-bit, the transition from moving outside of the 4 GB space was really impactful. Yeah, and then the operating systems ate up a big chunk of that, like almost 50% of that space. So how do we reduce that footprint? How do we make sure that it's not all contiguous, so we don't have to just go above the 2 gig bounds? And so that's what drives innovation and performance, and just some simple thing like large pages, right? In the hardware, how do we use that? What's the point of having 1 gig addressable space? What is the importance of having 1 gig large pages, and how does that affect performance? And how do we get applications like databases out there to use and be more impactful in performance by this 1 gig? What are these workloads out there that are going to use? So that's where it it's always been. That's where I have always straddled. Innovation sometimes, and we'll get into, in the book I talk about the bottom up and the top down, but it's about innovations no matter where you're driving it. Sometimes there's an application need, sometimes there's an ecosystem need, and sometimes the hardware our hardware architects understand that this is what we need. It's about, I was at ARM, and we always used to talk about parallelism,
Yeah.
so instruction level parallelism and data level parallelism. So we are doing innovation in these two spaces. How does the software take advantage of that? So with respect to concurrency, with respect to and just parallel working, optimizing the use of cores, and what does it mean? So it's just fascinating. There's so much out there, and I hope I've captured some, or at least I have made people curious with this book. I made people curious into understanding. Yes, there is a harmony that needs to be obtained here, and in chapter 5 dedicate this whole thing about harmonizing with hardware. What does concurrency mean? What are the primitives that we use? Because I want people to understand that nothing works in isolation, and a deployment is not done when you hit the deploy button. The deployment is like, the holistic understanding of where it gets to.
Okay. I want to read a part of your book here, and just have you comment on it here, right? And it's about experimental design, because I think one of the core activities, or an activity that's core to performance engineering, is benchmarking, and that, I think, all falls around what I would call experimental design. So, and you write here, experimental design is a systematic approach used to test hypotheses about system performance. It emphasizes data collection and promotes evidence-based decision-making. This method is employed in both top-down and bottom-up methodologies to establish baseline and peak or stress performance measurements, and also to precisely evaluate the impact of incremental or specific enhancements. The baseline performance represents the system's capabilities under normal or expected loads, whereas the peak or stress performance highlights its resilience under extreme loads. Experimental design aids in distinguishing variable changes, assessing performance impacts, and gathering critical monitoring and profiling data. So I guess, experimental design is core. And, so can you just elaborate on, what the message you're trying to drive home with that?
So I'm okay. So I'm going to try to break it down a little bit, but I am fascinated by this concept of pie charts, and I'm going to try to
Pie charts?
yes.
You like pie? I'm not sure about charts.
I love pie too, but the way it's about the sum of the components, right? The pie chart represents sum of its components, and then that's what makes it whole, and that's what I'm trying to capture in that long sentence. But it's that's what experimental design is about, So think of it like the complexity and the variables, right? Of course, the reproducibility part of it, like you design an experiment and it's not reproducible. So that's something that you have to keep in mind. You have to keep in mind the real world scenarios with respect to benchmarking. There's this whole component of noise and isolation, and how we can be true to the real world scenarios, but also work in an isolated setup just to make sure that we are producing. So this all works together. The trade-offs that
you're talking about load shaping.
yeah.
Also.
So it's kind of it's amazing that, and this is why I said pie chart, because you're not it's the sum of the whole, right? So for example, one of the main challenges in experimental design and benchmarking is managing the complexity, and then you have a multitude of variables that you have to that can influence the result, that will influence the result, and some of them, these variables, you don't even know. And this is why I was talking about integrating with the known knowns and the known unknowns, as in like the top down methodology and stuff like that. Because
that makes benchmarking difficult, and most of them are broken in some way. Most people get it wrong.
Exactly. There's so many talks like, was it benchmarking done wrong, or
Yeah.
are you benchmarking what you think you are? And this is, there was
And
this
even in
whole.
those talks, they're getting it wrong.
Well,
It's like, are
you and
you
I,
getting it wrong? It's like, yeah, and you are too,
so you and I have worked in this field, especially with benchmarking, for so long that, I tell people, if people wake me up in my sleep, and at least like it reminds me of my dad. Like, my dad would be sleeping and we get up at like 5 a.m. trying to ask him some questions because I have a submission or something coming up. If it's a math question, like anything, his eyes will be still closed and he will solve it. Like he
right.
was like that. You and I, Kirk, probably it's like the performance benchmarking. Somebody wakes up at 5 a.m. And they tell us to write a benchmark or do it right given the components and everything else. I think I can read.
Oh, I would get it wrong. There's no doubt about it.
I'm pretty sure you will. You will
Yeah,
get it.
I get it wrong.
I
I
know.
get it
I
wrong.
know.
Yeah.
I know you, and you're very
No,
meticulous
no,
in
no.
that.
Yeah, and even when you're meticulous, you're still going to get it wrong. I mean, it's just very difficult to get it right, and a lot of investigation, I think. Yeah.
But by the way, that's what experimental design helps you, right? Kind of you understand the complexity, the variables, and I think you do too, Kirk. And I think it's very humble of you to say that, but I've worked with you, so I know it.
No, I
The
I get it wrong. It's and it's not a. I don't think getting it wrong is not the problem. It's recognizing that it's wrong and then trying to understand why it's wrong and then making the corrections. I think is really the important thing, right? And I think that's the latter steps that you see get missed out on. So I think part of getting through the benchmarking process is recognizing that there's some problem here. And I guess now you're into a performance investigation, and you talk about bottom up and top down. Which one do you prefer? Do you actually mix them together? Like, how do you use these bottom up, top down designs?
So I think as you touched on, Kirk, benchmarking often struggles to simulate real world conditions, right? And when we're talking about experimental design, we're thinking about trying to capture some real world scenarios and with synthetic benchmarks, or kind of make sure that we're capturing the production workload and kind of being more realistic, more reputable, and you need to have some understanding, or at least a deeper understanding of the system and the workload being tested. So that brings us to the methodology and the approach, and that's where the top-down methodology or the bottom-up methodology. It's about how or where our knowledge lies, right? In the sense that when we talk about top down, we're talking about the highest level, that as in starting all the way. Remember, we started this conversation, we talked about user experience, right? And the overall system performance. So it starts all the way up there and then drills down into the details of identifying bottlenecks or areas of optimization. It kind of relies on the big picture of known knowns, right? We know what we know. We know about the application, we know about the ecosystem, we know about the libraries, we know, and sometimes we know about the user experience and expectations, and then we know about that we have a problem, right? Uh, as opposed to bottom up, where it starts from the lowest level, example code or system internals, and builds up the understanding of how these details impact the overall performance. It's like looking under the hood and then looking up to figure out how we can gain the impact. Like, remember, I was talking about large pages in hardware, all those things. So it's about a lower level detail, like even from the JVM perspective, designing garbage collector to be efficient falls into the bottom up methodology stack, And so we know the garbage collector, we're trying to improve its efficiency, whatever in the design of the garbage collector space. And then we want to look up and trying to see how we can benefit and what are the real world scenarios that are going to benefit from that. So kind of and most often than not, and Kirk, you have experience with that as well. These approaches are complementary, as in they're not mutually exclusive, and they're most often than not used together. You may start with a top-down approach to identify general areas of concern, or
Yeah.
and then switch to bottom up, and that's what it is all about.
I flip between them all the time. I'll use, top down to focus and bottom up to understand.
Exactly. And that's because it's switching from the bigger picture of what you know and then where you are, or what you're trying to improve. And it's always like, it's the different views that you can see, if you have a video call, right? You can
Yeah.
the room view or the individual speaker view, and that's what it is all about. And what these approaches, the methodologies tell us is how to approach the problem in a systematic
Yeah.
fashion, and when to use. I think one of the concerns that people have always asked me, like, when do we use one versus the other? So the top down, like I said, you're dealing with the system. You don't know there are unknowns that you want to peel out, and what those some of those unknowns are, but like you've identified a problem, and that kind of helps. If you have a statement of work and that guides you through, okay, known knowns, known unknowns, and stuff like that, and then the bottom up is we are already aware of the specific area that you need optimization. You already know a particular function is low, or you dive into the code or the system component, and it could be even at the hypervisor level. Something is happening that we're doing differently, or a scheduler at a scheduler level, OS level, scheduling effects. There's so much things, but we've identified, and now we want to drill. So kind of goes hand in hand with each other, but also those approaches are very tackle different problem spaces.
Right. So just in wrapping up here, I guess, what do you see as the future of performance engineering?
I think automation. Let's be honest, right? We are already there. We're talking about AI, machine learning, automated tools. I've had the pleasure of collaborating with various performance engineers who see that and who are contributing towards these kind of automated tools, and trying to understand real time issues and kind of prediction in a manner. And this prediction can be at different levels, active, passive, offline, but they kind of help guide the performance engineering effort. The future is also in the way we're evolving with respect to the hardware. Like, performance engineering is keeping pace with the hardware evolution with respect to accelerators. Now, I've in the last chapter of my book is dedicated to exotic hardware, which is like these kind of accelerators, and how the JVM, coming back to the crux of my book, is all about the JVM. So the future and how the JVM is evolving and getting into the space of being more compassionate with these kind of accelerators, and being able to address that new space. The evolving tool sets, new tools and methodology. You talked about it, Kirk, as well. We want to be able, the observability, all these advancements that we're doing in the field of performance engineering. Observability is at the heart of it, and we're only going to see it being much, much better. Focusing collaboration across disciplines. We're no longer data scientists alone and hardware engineers alone. We're not working in silos. We're collaborating. I want to learn. If you're a hardware engineer, I want to learn. I want to see your data engineering, the big data problem. I want to help you be able to, bring the performance engineer and learn from you, and bring the performance engineering expertise to between our domains, share them. distributed systems will always be complex in the sense that new technologies will always increase that complexity, add more layers to the complexity. But this is why we all need to collaborate across disciplines so that we help each other understand the complexity and make it easier for everybody to operate and coexist.
Well, thank you for your time, insights, and just the ability to just sit and have a nice conversation with you. It's really nice.
Yeah, thank you again, Kirk. I mean, I really appreciate you taking the time to read my book, first of all, and then also to ask these questions. It is an honor to be here. And thank you, Anka, for making this happen. I appreciate your effort. You're such a good friend, and I'm glad we all could be here.
Thanks for listening to this episode of the GOTO podcast. Head over to gotopia.tech to discover lots more content from the brightest minds in software development.